Welcome to section 1.4 Predicates and Quantifiers part 2, translating from English to logic. This is Dr. Gilbert, Eyabi. Example 1. Translate the following sentence into predicate logic. Every student in this class has taken a course in Java. Let's look at a couple of solution options. Number 1. If U is the set of all students in this class, then this would just be for every x, j of x, where j of x is x has taken a course in Java. Very often you do not want to restrict the domain so much, but that's a possibility. So if U is all students in this class, then we can define the propositional function j of x as x has taken a course in Java, and that becomes for every x, j of x. Remember that this is for every x. So for all students in this class, that student X has taken a course in Java. Or we could open that even more and define our universal set U to be the set of all people. Then we read the example as follows. If a student is in this class, then the student has taken a course in Java. So it becomes for every X, if a student is in this class, if X is in this class, then X has taken a course in Java. Now, on the other hand, if we go with this is something else altogether. For every X, if X is in this class, then X has taken a course in Java. But if you were to read it in this form, it would be everyone in the world is in this class and has taken a course in Java. That doesn't really work. Okay, so let's move on. Example 2. Translate the following sentence into predicate logic. Some student in this class has taken a course in Java. Again, if U, the universal set, is a set of students in this class, then it would just be there exists X, J of X. Again, the domain is too restricted. But if my domain is the set of all people, the universal set, then I could say there exists X, there is a student, such that, parentheses, the student is in this class and has taken a class in Java. To have the domain be broader is necessary, especially when dealing with multiple statements. Okay, so broader is necessary at times when dealing with multiple statements. For example, if a student is in this class, then the student has taken a class in Java, or the student has done this or that. So you want to make the domain as big as possible so that your statements would be very clear when you write them in predicate logic. What do you think this would mean? There exists X. S of X implies J of X. I would leave that as a SIVS, simple exercise for serious students. Okay, let's return to the Socrates example. Remember the example? All men are mortal. Socrates is a man. And then we came up with the conclusion that Socrates must be mortal. We would actually solve that officially using inferences, but right now let's put in some predicates. So introduce the propositional function man X, that means X is a man, mortal X, that means X is mortal, and then the two premises involving the Socrates example would be for every X, if X is a man, then X is mortal. And then we also know that Socrates is a man. That's the next sentence that was given. Right here, this is a specific example, and this is a general case. So if the general case is given, and Socrates is just an example that satisfies the general case, yes, we can conclude that Socrates must be mortal. Again, we'll do this officially using inferences. So later, we will show how to prove that the conclusion follows from the premises, and that will be done using inferences, like I just mentioned. Okay, let's talk about equivalence in predicate logic. Statements involving predicates and quantifiers are logically equivalent if and only if they have the same truth value. Number 1, for every predicate substituted into these statements, and number 2, for every domain of discourse used for the variables in the expressions. Let's break that down. S equivalent to T, that's our equivalence notation. So that indicates that S and T are logically equivalent. For example, right here on the left-hand side, that would be our S. For every X, not S of X. we have our quantifier, we have our predicate, and over on the right hand side, we have for every x, s of x. These two statements are logically equivalent. Of course, you can see this very easily. Not, kind of just destroy themselves nicely. And that becomes for every x, s of x. So we say that these two statements right here involving predicates and quantifiers are equivalent. Now, let's think about quantifiers in terms of conjunctions and disjunctions, and this should give you a good idea of what quantifiers are. For every x, p of x means that the statement holds for p of 1, for p of 2, for p of 3, for p of 4, for all x. Even if there are infinitely many elements in the domain, it holds for all elements in the domain. So for every x, p of x is simply p of 1 and p of 2 and p of 3 and p of 4 and so on and so forth right up to infinity. Now, if the set is finite, then it's a lot easier to view it as p of 1 and p of 2 and p of 3 and p of 4 and p of 5. If it's an infinite set, then we're looking at p of 1 and p of 2 and p of 3 n to infinity, and that gets very complex but exciting. There exists x p of x means it either holds for p of 1 or it holds for p of 2 or p of 3 or p of 4 or p of 5. So there exists x p of x simply means p of 1 or p of 2 or p of 3 or p of 4. Remember, there exists x p of x simply means there is an x value in the domain such that p of x is true. 1 is good enough. So that means it could be true when x is 1, it could be true when x is 2, or is very important, when x is 3, or when x is 4, or when x is 5, and if the domain is finite, then we have p of 1 or p of 2 or p of 3. If it is an infinite domain, it's p of 1 or p of 2 or p of 3 or, and it goes to infinity. Whereas, as we saw before, this would mean for every x in the domain, p of x is true. It is true when x is 1, and when x is 2, and when x is 3, and you can see and all conjunctions and disjunctions. And we would use this to verify some statements and logical equivalence involving statements that have quantifiers and predicates. Now, as mentioned before, even if the domains are infinite, we can still think of quantifiers in this fashion. But in this case, the equivalent expressions without quantifiers will be infinitely long. Negating quantifiers. How do we negate quantified expressions? For example, for every xj of x, how do I negate for every xj of x? Every student in your class has taken a course in Java. When would that be false? If I can find one student in that class who has not taken a course in Java, I would have negated that statement. For every xj of x is negated with just one counter example. How do we express this in logical expressions? Negating the original statement gives the following. It is not the case, or we say it is not true that every student in your class has taken a course in Java. Or we can say there is at least one student in your class who has not taken a course in Java. And it is very easy. So if I negate for every xj of x, what I get is, watch this very carefully, for every gets changed to there exist. X remains the same because that is just a student. J of x gets negated to not j of x. So every student in this class has taken a course in Java. If I hit my negation sign, it says it is not the case that every student in this class has taken a course in Java, or we can say there exists a student in this class who has not taken a course in Java. Again, if I negate this, for every changes to there exists, and j of x changes to not j of x. And let me show you how easy that is. If I write for every x j of x as it is expected, using conjunctions and disjunctions, for every x j of x will be j of x1, That means true for x1, true for x2. So that would be g of x1 and g of x2 and g of xn. If I negate all of this, I apply what is known as generalized De Morgan's laws. And recall what De Morgan's law would do. It would negate all the statements and then transform the and to all. So that would be not g of x1 or not g of x2 or not g of xn, which is simply there exists not g of x. So it's very easy to see this negation of the universal quantifier using the generalized De Morgan's laws. Let's continue. How do we negate there exists g of x? I'm sure you could already start thinking. If we negate for every and get there exists, if we negate there exists, we're going to get for every. For example, there is a student in this class who has taken a course in Java. When would that be false? That would be false if there is no student at all in that class who has taken a course in Java, i.e., for every student in that class, not g of x. Negate g of x. The student has not taken a course in Java. Negating the original statement gives, it is not the case that there is a student in this class who has taken a course in Java. In other words, every student in this class has not taken a course in Java. So if we negate there exists g of x, we get for every x, not g of x. Again, applying our generalized De Morgan's laws, there exists x g of x will be g of x1 or g of x2 or g of xn. And using generalized De Morgan's, that becomes not g of x1 and it all changes to and, not g of x2 and not g of xn, which is simply for every x, not g of x. So when we negate there exists x g of x, we get for every x, not g of x. And that's very important when it comes to proofs. How do we prove that there exists x g of x is not true? We have to prove that for every x in the domain, g of x is not true. How do we negate for every x g of x? Find an element x such that g of x is not true. And here we have the table. I expect you to remember this table. So if I negate there exists x p of x, I get for every x not p of x. And if I negate for every x p of x, I get x. There exists x not p of x. Okay? So when is negation true? When is it false? So this is the reasoning. What we are saying is for every x p of x, if it is negated, that is equivalent to there exists x not p of x. Just remember this. For every changes to there exists, p of x changes to not p of x. If I negate there exists changes to for every, and p of x changes to not p of x. That's it. These are very important rules and you will use these again. You will see them again. So make sure you remember the negation of these quantifiers. Of course, it gets really interested when we start negating nested quantifiers. We'll follow the exact same procedure. What if we have for every x, there exists y for every j as one statement and we negate all of that? What happens? All the for everys become there exists, all there exists becomes for every, and it gets really beautiful. Translation from English to logic. Example 1. Some student in this class has visited Mexico. If you have just one statement, you could actually make your domain as restricted as you want, but it's always advisable to leave your domain as broad as possible because you could have a couple of statements put together. So if our domain is the set of all people, then m of x would be x has visited Mexico and s of x would be x is a student in this class. So it will be there exists x such that x is in this class and x has visited Mexico, and that becomes our translation. I would expect you to be able to translate from logic involving predicates and quantifiers back to English, and we'll do that later. So there exists x such that x is a student in this class and x has visited Mexico. Now, example 2. Every student in this class has visited Canada or Mexico. I could interpret this as if a student is in this class, then the student has visited Canada or Mexico. So why don't we add C of X to mean that X has visited Canada? Then we would say for every X, remember our domain is a set of all people, so we have to be very careful how we translate this into logic. So for every X, for every human being on planet Earth, parentheses, if X is in this class, then X has visited Mexico or Canada. See the translation? Now what I want you to do is see if you can restrict your domain to just be the set of students in this class and try to rewrite these two English sentences into logic. Or to be more precise, these two English statements or propositions into logic. Here we have some fun with translating from English into logical expressions. I would actually let you play with this. U is the set that has just three elements. Here they are: f of x, s of x, t of x, and then we have a couple of translations. Everything is a fligel. How do we translate that? Very straightforward. What about more exciting translations like this? And I'll let you play with this all by yourself. Okay, very good. So take some time and play with this, and let me talk a little about Lewis Carroll, Charles Dickens, and Ludwig. Many of you may not know much about him, but he is the guy who wrote the book Alice in Wonderland. Yes, he was a logician, and there's a lot of logic involved in all his books, even Alice in Wonderland. Okay, what he usually does is he'll give a couple of premises, and he would expect you to come up with a reasonable conclusion that uses all the premises. We'll do a lot of that in class. I'll give you a couple of problems to solve. Actually, your first take-home graded quiz would be examples from Lewis Carroll's book on logic. So let's look at this one. All lions are fierce. Some lions do not drink coffee. And a conclusion from that is some fierce creatures do not drink coffee. Again, all lions are fierce. Whenever you see all, you could translate that as if you are a lion, then you are fierce. Okay, we will do a lot of translations once we go through inferences. Right now, we would just leave things hanging a little until we go through inferences. Here is one way to translate these statements to predicate logic. Let P of X be the statement X is a lion, Q of X the statement X is fierce, and R of X the statement X drinks coffee. Then the first would be, recall, we like you to interpret this as if you are a lion, then you are fierce. And that would make translation very easy. So it would be for every X, if X is a lion, then X is fierce. So for every X, parentheses, P of X implies Q of X. Next, some lions do not drink coffee. You want to see it as there exists a lion. There is a lion that does not drink coffee. So there exists X. There is a lion. There exists X such that X is a lion and X does not drink coffee. There is a lion that does not drink coffee. And then the conclusion, some fierce creatures do not drink coffee. So there exist some creatures who are fierce and they do not drink coffee. And we shall see later on from the laws of inferences that we can use premises 1 and 2 and come up with a reasonable conclusion. And that is exactly what we are saying here. Later, we will see how to prove that a conclusion follows from the premises. And that will be very, very exciting. Okay, thank you very much. That brings us to the end of part 2 of section 1.4. Predicates and Quantifiers, and I will see you in section 1.5, 1.6, 1.7, 1.8, where we start dealing with proofs. Thank you and God bless you. Bye-bye.